In section 3.1, we're looking at the derivative of a function. Now, first of all, the derivative is something that we've been using before. It's basically talking about the instantaneous rate of change. So when we calculate the derivative, we're going to be calculating this using the same formula that we used for instantaneous rate of change in the last chapter. So that shouldn't be unfamiliar to you. You should be able to do that already. What we are doing is we're giving it a different notation and a different vocabulary for the derivative. And so we're going to need to know how to use that vocabulary and notation correctly. And then finally, we're going to be looking at how to graph a derivative just by looking at its graph. So this is probably the part that's most difficult. So if you're given the graph of a function somewhere, you're going to need to know how to graph the derivative, or if you're given the graph of the derivative, how to graph that original function. First of all, defining the derivative then, notice this is defining it as the instantaneous rate of change. We're just not saying slope anymore, we're saying f prime of x. So this notation f prime of x equals, is saying the derivative of what we had for f of x is equal to f prime of x. And the nice thing about that then, by keeping it in terms of x, we can plug in any value. Say I want f prime when x is equal to 3, and I can find the derivative at that point. Now, if f prime exists, if we can find an equation there that works out, we say that f has a derivative. Now, if we can find a derivative at every point in the domain, because maybe we can only find it at certain values, but if we find it for every point in the domain, we call it a differentiable function. So here's an example of finding a derivative. This one is very much like what we did in the last chapter. We want the instantaneous rate of change, what we call it f prime of x. We plug in our function, we simplify it, and this ultimately works out to 2x. So we can say that the derivative of f of x, or f prime of x, is equal to 2x. I can plug in any value that I need to find at that point. Now the notation, the correct way to write it, we just saw that we can write this as f prime of x, but there are other ways to write this. If we were given an equation like y equals whatever, x squared, then we could say y prime. So it's very similar to using the f prime notation. We can also use this notation, dy dx, which is very similar to thinking of this as a change in y over change in x, which would be our slope. But by using d, we're talking about differentials. So infinitely small changes is what we're talking about in this one. And so that kind of gives the idea of h approaching 0 there. This is similar to the last one, but we're using f. Usually we're going to see the dy dx. Now notice how this one is different from the previous. This just says d dx. It doesn't have the y in there. This one's actually an operator. This is telling us take the derivative of whatever follows this. As an example, we look here, if my function is y equals x squared, we saw that before, we know that from that previous example that this came out to 2x. If we say d dx, we need to follow that with a function that we're going to take a derivative of. So the derivative of x squared is 2x. If I say dy dx, it means I'm referring to an earlier function. Whatever my function y is, I know that my derivative is 2x, my derivative with respect to x. Next, we're going to be looking at, if we start with the graph of a function, what would the graph of its derivative look like? So we're going from the graph of f, or just y here, to the graph of f prime, or here y prime is what we're trying to do on this side. So what we can think of the derivative in graphical terms is the slope, or the slope of the tangent line, really. So if we estimate the slope of the tangent line at different points along the graph of f, then we'll be able to estimate those values of y prime. So basically what we're doing, we look here at this first part, this first point, and I estimate that the slope is about 4 at the point when x is 0. So when x is 0, our slope is 4. I move over to 1, and I'm estimating that that slope is about 1. At 2, we could estimate that slope as 0. At 3, it looks like negative 1. At 5, it looks like it's negative 1 again. At 6, it's back to 0. And we could keep going, but this gives us a basic idea. And then we think of the slope, rather than calling it slope or instantaneous rate of change, that's going to be our y prime or f prime. And so I can graph these on a graph of x y prime axis as my x value and then the slope. So 1, 1, 0, 4, 2, 0, 3, negative 1, 5, negative 1, 6, 0. And then basically I connect the dots in a nice smooth curve to get an idea of what's happening. So if I look here at 4, for example, it looks like we're down at about negative 1.25. So even though I don't have that marked on here, I could estimate that slope at an instant, or the slope of that tangent line, as negative 1.25. I can also graph f from f prime. So here I have a graph of f prime. And I want to graph f of x over here. So I look here, if I look anywhere less than 1, then I see that my slope is negative 1. Because this is f prime. It is the slope of this graph. Up here I have a slope of 2. Okay, now don't get confused. Yes, this is a slope of 0 here, except that slope is equal to f prime. So really this graph here is telling me what is my slope for this graph down here, the graph of f of x. Now we have to look at these different properties. First of all, they have to give us the starting point, otherwise we can start wherever we want to. So we need that starting point 0, 0. They also tell us this is continuous for all of x, so everything we draw is going to be connected to this. Okay, now using this graph over here, since I'm at 0, maybe I'm going to start at this side. It's telling me I have a slope of negative 1. So I draw a line that has a slope of negative 1 here. Now, let me try that again. So I draw a line that has a slope of negative 1 here, passing through the point 0, 0, and I keep going until I get to 1 because that's where I have a change in slope. Now this is where it's important that f is continuous for all of x. I'm going to continue now with the slope of 2, and so I make the next side of this have a slope of 2. If this was not continuous, it might jump, and I need to know that it's continuous so that I know that I can just continue following from that same point. There's a better picture of that graph. In this example, we want to try to match these slopes. You say y prime, y prime. So all of these are the derivatives up here, and down here we want to match it to the original function. So I'm going to start with b, actually. Notice that our slope is always increasing. Well, so our slope down here is negative, and then here our slope is 0, and then our slope is positive. Okay, that's important because if I have a slope that's negative, that means I'm going down. Slope of 0 tells me I have a horizontal. A positive slope tells me I'm going up. So I'm looking for a graph down here that's going down, has a slope of 0, and then goes up. That would have to be number 13 here that goes with B. Okay, next I'm going to look at A. Notice, first of all, my slope, except for here, it's always positive, but I do hit a 0 right here. Okay, that means that I'm always increasing, except somewhere right about here, I have a slope of 0. So I'm looking for, first of all, functions always decreasing. No, this one's not always decreasing, goes up and down. This one goes up and down. This one is always increasing. So this one would have to be A. And we can know what's happening here at 0. Notice we do get a horizontal tangent line at that point. For the next one, we're going up, we get a 0. But our slope is negative, then our slope is positive. We're only worried about positive or negatives when we're calculating these. Okay, that's the only thing that matters. I'm going down, I'm going up, I'm going down, I'm going up. So we need to start by going down. 16 starts by going down, then it goes up. At 0 it goes down again, then it goes up. And so we've got all of our changes that we need. Really this point, this 0 here, we're going down until we get to here. We're going up to here, down to here, and then up after that. So that's going to match with C. Finally, we're positive, we're negative, we're positive, we're negative. We're looking where starting with the zeros, and then thinking what our signs are: positive, negative, positive, negative, positive. So these are all positive values, these are all negative values. This positive value tells me I'm starting by going up. The negative tells me I'm going down. Then I'm going up again. From 0 to here, I'm going down, okay, until I get to this point. Then I'm going up for the rest of the graph. It kind of levels out at the end. This one would have to be D. Again, the most important thing when we're looking at f prime of x is whether it's going up or down. So we're just looking positive values of y prime or negative values of y prime. We can also have one-sided derivatives. Notice how this is written as saying h approaching 0 from the positive side or h approaching 0 from the negative side. This might be important in, for example, an absolute value function where I have a different slope on each side, or it might be important for a piecewise function where I might or might not have a different slope on either side, and we want to find out if they are coming together. In this example, we'll be looking at one-sided derivatives of a piecewise function. We want to show that it has a left-hand or right-hand derivatives at 0, but not necessarily a derivative there. So to look at a left-hand derivative of 0, we're looking at what's happening at negative x, because left-hand would be less than 0. Now, when we plug it in, we're still going to use 0 as my x value, looking for the derivative at 0, but we're using the left-hand side. Basically, we're using the function that's coming in from the left. And when I simplify that, it's going to come to negative 1. On the right side, we're going to use, again, we're going to use the point 0, but we're going to be using the function that's coming in from the right. And so I'm using h approaching 0 from the plus, and again I'm plugging in 0, but this time I end up with a positive 1 when I simplify this. So we notice that on one side we're getting a negative 1 slope, on the other side we're getting a slope of 1. Now notice what this function is. This is really the absolute value function here, where the negative side everything's going to change sign, on the positive side everything's going to change sign. So at 0 we get the bottom of our v here. So we have a negative 1 slope on one side, positive 1 slope on the other side. And since they're coming to a point where they disagree, we don't have a slope at that point. So we'll say that the slope is not differentiable at 0.